Okay. So we're going to continue notes from last time. Last time we ended off here. We talked about solutions. Okay, we talked about how a solution is made of solute plus solvent makes a solution. Okay, a solute is the component with lower concentration, and a solvent is the component with higher concentration. Okay, now they're going to be in the same state of matter. They have to be in the same state of matter to make a solution. A solution is a homogeneous mixture, meaning it looks the same throughout. Homogeneous mixture of two or more substances in a single phase. Okay, so you can put a liquid and a solid together, and then they come together and form a solution. That works just fine. They just form a single phase. You can also have two liquids that come together and form a solution. You can also have two metals that come together. Remember, we talked about metals. If metals come together form a solution, we call them alloys. And then gases can also form solutions as well, like air is an example. Just a mixture of different types of gases. Okay. We can have saturated solutions, so that contains maximum amount of solute. Unsaturated, which has a little bit less than the maximum amount. And we can have supersaturated. So supersaturated, you start at a higher temperature, a saturated solution at a higher temperature, and then you cool it. And as you cool it, it actually all the stuff stays dissolved in the solution, but it actually is higher than its actual saturation point. That's where we kind of left off last time. Okay, and then we're going to continue on here today. So first thing is the rules for solvation. So the rules for solvation, the general rule is that like dissolves like. We're going to talk more specifically about this tomorrow, probably. We'll get to it, where we will talk about exactly the solubility rules. We'll talk about the solubility rules. Today, we're just going to really talk about the principle behind it, just really quickly. So like dissolves like. So polar dissolves polar, and nonpolar dissolves nonpolar. So the more alike the solvent and solute particles are, the more likely they are to dissolve one another. Okay. The reason for that is because the solute particles and the solvent particles are attracted to one another. In order for them to mix with one another, those solute particle intermolecular forces and the solvent intermolecular forces have to kind of be broken temporarily, that they'd be broken temporarily. And they won't be broken if the solvent-solute particle interactions are not similar. They're not similar. Okay. So if particles of solute will dissolve if it is more attracted to the solvent than to itself. Okay. If it's more attracted or similarly attracted to itself, to the solvent particles. If they would rather, if they have more attraction to one another, then they're just going to stay with themselves, right? If the solvent and solvent particles are more attracted to each other than to the solute particles, they're not going to break apart. They're not going to intermix with the solutes. Okay, so that's the general rule. Okay, we'll talk more about solubility rules and exactly how that works later on. We'll see, maybe we'll get to it tomorrow. I'm not really 100% sure. Okay. Factors that affect solubility. So there's really, the first one is the type of solute and solvent. So like we just said, the like dissolves like. That's the biggest factor. That's the biggest factor. The next one is temperature. So temperature, solids will typically dissolve more readily at higher temperatures. Okay, so solids will dissolve more readily at higher temperatures. Let's get this going here. Come on. It never likes to play when I'm taping this, so let's see if it'll play. There we go. So solids will dissolve more readily at high temperatures. So if you have a solid in a liquid, you're going to get more dissolving at higher temperatures. Okay. Now gases are the opposite. Gases will actually dissolve more readily at lower temperatures. One of the situations I always talk about is if you take, I don't know if anyone's ever taken like a hot soda. You have a soda that's been sitting out a long time and it's, just in the warm air, and you try and open it, it will like go psh, and it will, overflow. That's because the gases are less soluble in warm water or warm soda. Okay. So gases actually are opposite of solids. So this is a little bit confusing, but if you think about it, if you're heating up a gas, gases have more energy, more kinetic energy. They want to escape to the gas phase, right? They don't want to be in solution. They want to escape into the gas phase. So the hotter the solution is, the less likely the gases are to dissolve in it. The opposite is true with solids. If you have more kinetic energy, that means the solvent particles have more energy and they have more ability to kind of move and break apart those solute interactions. So really, it's only two things: like dissolves like, and temperature. The next one, pressure. Pressure will only increase the amount of gaseous solute that can be dissolved. So pressure, if you increase the pressure, you increase how much gas can be dissolved. However, it has no effect on the solid. Okay, so no effect on the solid. You have to be a little bit careful here because agitation, which means like shaking or stirring, they can speed up the dissolving process, but they do not affect the total amount that can dissolve. They do not actually affect the solubility. Okay. The more you shake or stir something, the more it will dissolve, but the overall amount that will dissolve won't change. So the overall amount won't change. Yeah. Okay, so let's talk about in solutions. We can have two types of solutes. We have two types. Well, I guess three types because we could have gases too, but we're not going to talk about gases too much. Okay. When we're talking about solids in solutions, there can be two types. We could have non-electrolytes and electrolytes. Okay. Now, really, two types of things dissolve in solution or in water, in aqueous solutions. Okay, we're talking about this non-electrolytes and electrolytes. We're actually talking about aqueous solutions. We can have two types. We can have something that breaks into ions, and we have something that's polar or slightly polar. Okay, so the slightly polar molecules, those are non-electrolytes. They do not break into ions. Okay, so that's a non-polar molecule, sorry, a polar molecule dissolving in water. We get an aqueous solution, and they will not conduct electricity. Okay, they will not conduct electricity. We call those non-electrolytes. Example of that is something like sugar. Okay, sugar dissolves in water. However, it does not break up into ions. The only reason it dissolves in water is because it's polar. It is polar and water is polar. So it will break up, or not break up, but it will dissolve in water, but it will not conduct electricity and it doesn't break up into ions. Electrolytes are solid solutes that break up into ions. Okay, so these are typically salts. So salts, they go into water and they break up into positive and negative ions. And when they do that, they can conduct electricity in water. So if you put salt in water, it conducts electricity. If you put sugar in water, it does not conduct electricity. So non-electrolytes and electrolytes. Okay, these little symbols, so you see this like S and this AQ. S means it's a solid, AQ means it's aqueous or in water. It's in water. Okay, you'll notice that if you take sugar and you put it in water, it stays the same, does not break them to ions, whereas sodium chloride, table salt, it starts as a solid, you put it in water, it becomes ions in solution. Okay. There's also two types of electrolytes. There's weak electrolytes. Weak electrolytes only partially dissolve, or partially dissociate or break apart. So some of them, if you have something that goes in water and it's a weak electrolyte, some of the particles will break apart into positive and negative ions, others will not. Okay, just that the strength of the intermolecular forces are really here, the strength of the ionic bonds are stronger than the attractive forces between the water and the ions. Okay, so they're relatively similar. Since they're relatively similar, not all of them break up into ions. We call that a weak electrolyte. Not all of them break up. Strong electrolytes, they totally dissociate or break apart in solution, and they conduct electricity well. So something like potassium chloride breaks apart all into ions, and it conducts electricity very well. And this one, the low conductivity, the weak electrolytes, that's acetic acid or vinegar. Vinegar. This is vinegar. Vinegar is a weak electrolyte. Okay. Acetic acid, vinegar, same thing, different names. Okay, so again, let's talk about when something dissolves, either two things can happen. So we can have dissolution. So like again, going back to that sugar versus sodium chloride or sugar versus salt. Okay. So when something dissolves, it can either stay all together, okay, so it does not break up into ions. Okay, they don't split up, but it does dissolve because the intermolecular forces are broken. Okay, the forces between sugar molecules, so one sugar molecule and another sugar molecule, those are broken, and new forces between sugar and water, so new intermolecular forces between sugar and water are formed. That's called dissolution. And basically, water molecules are just coating this. You'll just have water molecules surrounding this molecule. Okay. Whereas in dissociation, so you have this word dissociation, it means breaking up ionically bound molecules. Okay, so sodium chloride, Na plus and Cl minus, okay, they will break up into Na plus and Cl minus in solution. Okay, and then the Na will be surrounded by water molecules, and so will the Cl. Okay. So dissolution and dissociation. Dissolution means that they are just being coated in water. Okay. So sodium chloride undergoes both dissociation and dissolution. Undergoes both. Whereas sucrose or sugar only undergoes dissolution, not dissociation. Okay. So if you have an electrolyte, it will dissociate first, then undergo dissolution. Whereas if you have a polar molecule, it will just undergo dissolution, no dissociation. Okay, so let's talk about a little bit about salts. So there's different properties of salts and water. So we can have something called a salt hydrate. So typically salts, when you see them in the past, you've always seen like cobalt chloride, CoCl2, right? Now, this salt, we call it anhydrous. Anhydrous meaning it has no water in it. There's no water in it. However, some salts can absorb some water and stay a solid. Okay, they'll have some water molecules attached to them, kind of surrounding them, but they're not in solution. Okay, they're just kind of wet. It's just like, the difference between if you jump in a pool, you're basically like a solution, right? You're surrounded by water. But when you come out of the pool, you're soaking wet, yeah, well, you're not surrounded, you're not in solution. So think of like salt hydrates as they're not in the pool, but they're soaking wet, right? They're just like surrounded by water. They're covered in water. They're covered in water. That's what a hydrate is. Okay, a hydrate is. And then when you go into solution, you can think of that as like jumping in the pool and being surrounded by water. Okay. Now, when you take that towel and you dry off, and now you have no water on you anymore, that is anhydrous. You don't have any water surrounding you anymore. So you can think of that as anhydrous. Okay, so maybe I'll put that analogy in there somewhere. It's a good analogy, I think. So in solution, like you're swimming in the pool. You're hydrated, that's like you're soaking wet coming out of the pool. Anhydrous is like you're dried off, you have no water on you at all. Okay. And you're the salt. You're the salt. Okay, so anhydrous salts and hydrated salts. So you'll see it like COCl2 with a little dot and then 6H2O, meaning that each COCl2 molecule is surrounded by 6 water molecules. Okay, each cobalt chloride molecule is surrounded by 6 water molecules. That's a hydrate. That's a salt hydrate. Okay. A desiccant is a salt that is able to remove water from air. Okay. Anyone ever see those little like packs that come in like shoes or clothes or any really items that you buy? You'll get these little packets. There's little like packets. Maybe I'll put that in there too. Let me write some notes here about what I should add to this. Desiccant packets. Pool analogy. I'll add those things to it too. But a desiccant is a salt that is able to remove water from air. So you'll often see them little desiccant packets and some items that you buy in the packaging because it removes water, keeps mold from forming or from the things from breaking down. Okay. A desiccant contains a hygroscopic salt. A hygroscopic salt is a salt that can take water from the air. So it actually removes water from the air. So if there's water in the air, the hygroscopic salt will absorb that water. Okay. Now, a hygroscopic salt that takes in enough water to actually make it into a solution, we call that deliquescent. One of my favorite words in chemistry, deliquescent. Okay. A deliquescent salt can take enough water from the air to make it a solution. So here is an example. Here is sodium hydroxide little pellets in this blue plate here. If you let it sit out long enough, it will actually absorb enough water to create a solution. It'll just keep absorbing water. Okay, so sodium hydroxide pellets, I have this in my lab, and I have to make sure that I close the bottle very, very tightly. I usually put some plastic, actually, I put some like plastic wrap kind of stuff. It's not plastic wrap exactly, but that's kind of what it is, around the outside of the bottle actually to help keep the moisture out too, so it doesn't turn itself into solution. Lithium chloride is actually even worse than sodium hydroxide. Lithium chloride is, oh man, that stuff deliquesces really, really easily. It turns into a solution. Turns itself into solution just by sitting out for a little while. It's crazy stuff. Okay. The opposite of deliquescent is effervescent. So there's also hydrates called effervescent that lose their water to the air. Okay. Even in a super moist air environment, the effervescent hydrates will lose water to the air. The opposite of deliquescent. Okay. Okay, now let's move away from solutions and from salts and talk about other mixtures. So homogeneous mixtures look the same throughout. So that's what we've been talking about with solutions. So solutions look the same throughout. We call them homo, homo meaning the same. Some examples: coffee, wine, air, brass, blood, vinegar, natural gas, steel. These are all actually solutions, really. They're all solutions, okay? We also have heterogeneous mixtures. Heterogeneous mixtures, you can see the different parts in them. So like chocolate chip cookies, pizza, soda with ice, tossed salad, sandwich. Well, those are all delicious heterogeneous mixtures. Okay, hetero meaning different. Homo meaning the same, like homosexual, same sex. Heterosexual, different sex. That's where the word comes from. Okay. Okay, other mixtures. So there are other types of mixtures that are not necessarily solutions, right? There's colloids. So you have a heterogeneous mixture, so you can see the tiny, tiny, tiny little particles. The particles are larger than solutions, but smaller than suspensions. Sometimes you can't actually see them with your naked eye. It may look like the same throughout, but one way you can notice that there's different particles is you shine a light through it. So in a solution, if you put a light through it, light can pass through it and you won't see anything, okay? In a colloid, if you put light through it, it'll scatter it and you'll actually see the little parts to it. And then in the other one, a suspension, if you shine a light through it, you can see the particles and sometimes the light cannot pass all the way through it, okay? So in a suspension is a heterogeneous mixture that is particles suspended but will come out of solution if left undisturbed. Okay, so if you let it sit for long enough, it'll become two parts. Okay, and really it all has to do with the particle size. So solutions have the smallest, colloids have it somewhere in the middle, and suspensions have the largest particles. So this little chart kind of helps a lot. Distinguish the difference between solution, colloid, and suspension. Okay. Again here, solution, colloid, suspension. The particles, you'll see that the light will scatter. You can actually see the beam of light. Okay, and then a suspension, you can actually see the beam of light and you can see the little particles floating through it. Okay, this is an example right here. Solution, beam goes right through. Colloid, you can see the beam slightly, and then a suspension, you can see the beam very, very well, and it doesn't even really pass all the way through. It doesn't even pass all the way through. Now, this effect of the scattering of light by the particles, we call that the Tyndall effect. Okay, the Tyndall effect. And typically we only say that happens in a colloid, but it does happen in suspension sometimes too. But typically we'd say that suspensions will have large enough particles that prevent most of the light from going through. Most of the light. Okay. And that is it. That is all I wanted to talk about today. So hopefully you were able to follow along with that. And you should be able to answer all of these questions, fill in the blanks. Okay. And that is all I have for today. Okay. So your job now is to make sure you finish this if you didn't finish it while I was going through the notes. All right. And I will see you all tomorrow.